So let's take a look at our square root and cube root functions and their graphs. So first thing we're going to do is just complete a table. So with this table we have these values for x, and we're filling it in for our function, the square root of x. So what I can do is think of, okay, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. Notice the table didn't plug in any negative numbers, and that's because we can't plug in negative numbers. So if I did have this table go back further, what we would see is a bunch of undefined solutions. So our graph starts at 0, 0, and then I can plot our other points. So if we go to our graph here, we have 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. Now what I'm going to do is connect these, and it's going to be curved, so I'm going to connect them with a smooth curve. It's going to continue on. Now, I don't have anything being graphed over here, so it just starts right here at 0, 0, and then goes off to infinity. So for the domain, starts at and includes 0, and then goes off to positive infinity. For the range, same thing. So for the domain, in terms of x values, starting at x equals 0, and then we have x values that are positive, so that can be plugged in. For the range, our output starts at 0, and then we only have positive outputs for our function. Let's look at our cubic function. We're going to revisit that. I'll talk a little bit more once we see the shape of our cubic function. So, cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. So with that, we get a few points here. So at negative 8, we have negative 2, and negative 1, 0, 0, 1, and 8, 2. Alright, now with this, it's going to be a smooth curve. Even though it looks linear here, it's not going to be made up of separate lines. When you have different rates of change like this, that means it's going to be a smooth curve or a polynomial. So with that, we'll have something like this. I'm going to try that one more time. That didn't do very nicely. Okay, through here we're going to see something like this. Something like this. Yeah, a little better. Alright, there's our cube root function. So for domain, we can plug in absolutely anything. And for range, we can get absolutely any output. So with that, it's all real numbers for both. So negative infinity to infinity, negative infinity to infinity. So, we talked about this in simplifying and so many times, but with odd functions, so even though this is the graph of the cube root, this would be true if that was a 5, a 7, our domain and range would stay the same. So with that, we can plug in anything and get anything out. We can have negative results or positive results. Notice with our square root function, in terms of input, in terms of x, we can't plug in negative numbers. So we can't let x be a negative number. What we also can't have is in terms of output, we can't have a negative result. And that's something I brought up before when we were solving our equations and getting an extraneous solution. Having a square root equaling a negative number can't happen here. And this shows it. If we have our square root function, we can't get these output values that are negative coming through. So those are the restrictions of our graph. Now what I want us to do briefly is think about the graphs that we looked at for polynomials. We talked about this kind of general behavior of x squared, x cubed, x to the fourth, x to the fifth. Now, what I want you to remember is the shape of our x cubed graph, or really x to any odd power, and the general shape of the graph being our cubic function, which looked like this. Now that should look familiar here. It's just twisted onto its side. It's because these are inverse functions, which is something we talk about more in our next course in the algebra sequence. So you don't need to worry about that term too much, but it's the fact that we've used this while solving, the fact that this kind of cube root of x undoes the cube of x. Like there's this relationship for how they work together. They're very closely related, and with that we see a similarity in the graphs coming through. Now it's a little trickier with our square root function, because if I think about our x squared function, that would give us our parabola. So something like this. And the relationship is there, but if I did that same thing of just flipping it onto its side, then my graph would really go something like, well, better than that, but something like this. But what's wrong with that picture? It's not a function anymore, and we're working with functions here. So if we graph that entire thing, it becomes not a function, and we can't use it. What we have here is half of a parabola on its side. Basically, it's this part of the parabola twisted onto its side. So there is a relationship in shape, because like we have our 2, 4, our 3, 9, our 4, 16, those values are there. It's just our x and y coordinates are switched between x squared and this cube root of x. So I just want to make sure we notice the relationship in the graphs and these kind of basic forms of our functions and how they relate to our polynomial functions.